Hello students, let us complete the small portion which was left behind in the chapter thermodynamics. The topic is heat capacity. So, three types of heat capacity you will be learning here. One is just heat capacity, another is molar heat capacity, and thirdly, specific heat capacity. So, how we define heat capacity? It is the amount of heat required to raise the temperature of a substance through 1 degree. So what we understand here, you can take any amount of substance at any temperature and you increase the temperature just by 1 degree. Okay, say you have taken a certain amount of substance at 25 degrees Celsius. You heat it in such a way that the temperature becomes just 26 degree. So during this process, how much heat is absorbed by the system, that much heat is called heat capacity. Okay, but it is not always possible for us to maintain 1 degree, so we can do the calculation by using unitary method also. Let us assume that Q is the amount of heat required to raise the temperature of a substance from T1 and T2. So here the T2 T1 difference need not be 1 degree. We are taking any situation where we have taken certain amount of substance, we have given Q amount of heat, and the temperature has rise to Q2 from Q1. Now, more will be the quantity, more will be the, sorry, more heat you give, more will be the rise in temperature. So we write Q is directly proportional to delta T, where delta T is T2 minus T1. Now to remove this proportionality sign, you need to bring in a constant, and that constant is C. This C is called heat capacity. Now you see here the value of C can be defined as C is equal to Q divided by delta T. That means if delta T is 1, that means if the rise in temperature is 1 degree, then the value of C is equal to Q. So how we define? So now you can correlate with the definition. Heat capacity is the amount of heat required to raise the temperature of a substance through 1 degree. So you can understand, if the quantity of a substance is different, same substance, if I take different quantities, the amount of heat required to raise the temperature of the same substance through 1 degree in two different cases where the masses are different, the value of C will be different. That means you can understand the value of C depends on the mass of the substance, as that is why we call it extensive property. Now you can see here that C is inversely proportional to delta T. So for any substance with high heat capacity, rise in temperature will be less. For your information, let me tell you, water is having a very high heat capacity, and that is why it takes long time to raise the temperature of water. Next we move to molar heat capacity. As the name suggests, you can understand, it is defined as the amount of heat required to raise the temperature of 1 mole of a substance through 1 degree. That means here we are specifying the quantity of the substance. Whatever substance we take, that has to be taken in 1 mole. And it is represented by the symbol C subscript M, where M stands for mole. And you know, it can be calculated from specific heat by dividing the number of moles in certain quantity of a substance. So Cm is C divided by N. Now specific heat capacity represented by small c. It is defined as the amount of heat required to raise the temperature of unit mass. Now here it is neither unit mass means it need not be mole. You can take 1 gram, you can take 1 kg, okay, of a substance through 1 degree. So if I write the mathematical formula for Q, Q will be equal to C into small m into delta T, where small m is the mass of the substance taken. because small c is for 1 kg or 1 gram. Now if you take 10 grams, then you have to multiply by 10. Now c into small c into small m gives you capital C, that is heat capacity. Okay. Now you may note that since molar heat capacity and specific heat capacity, the mass is already fixed. You cannot change. You have to take either 1 mole of a substance or you have to take 1 unit of mass of a substance. So the value of molar heat capacity and specific heat capacity becomes fixed. They do not change for a particular substance. That's why it is called intensive property. Now we move to a very important derivation. Derive the relationship Cp minus Cv equal to R. Now what is the meaning of Cp? The meaning of Cp is heat capacity at constant pressure. Cv is heat capacity at constant volume. And Ru, as you all know, it is the universal gas constant. So let us consider that the heat capacity C is denoted as Cv at constant volume and Cp at constant pressure. At constant volume, so if I apply the formula, Q is equal to C delta T. So here we get QV equal to CV delta T. And if you remember when we did first law of thermodynamics, we learned that QV is nothing but delta U. So we are bringing in delta U. What is delta U? Delta U was change in internal energy. So we label it as equation 1. Similarly, QP will be Cp delta T just from this equation. Okay. Qp equal to Cp delta T, and that again from enthalpy change, if you remember, that was given as delta H. So we label these equations as equation 1 and equation 2. Now from ideal gas equation, what we know, delta H is equal to P delta V, if you remember. And we also know that delta H is equal to delta U plus delta Ng RT. But since we are considering for 1 mole, okay, that n is becoming 1, so we are taking only R delta T. We cannot take delta R, remember, R is a constant, so it will not have variation. Now we replace the value of delta H from equation 1, no, from equation 2 by Cp delta T, the value of U by Cv delta T, and R delta T is already there. So we have already almost got the equation. Now you bring the C terms in one side. So we have Cp delta T minus Cv delta T equal to R delta T, from where we take delta T common. So when we take delta T common, we get a delta T cancelled from both sides. So that's how we get Cp minus Cv equal to R. So this derivation might be asked for 2 marks in the board exams. Okay, and it's very easy to derive. So you practice once or twice, you'll be able to do it. Thank you. That's how we conclude thermodynamics.